Hi, my name is Felipe and it's my pleasure to be here presenting our work, the plunging of Hyperpycnal Plumes on tilted bed by three-dimensional large-eddy simulations, together with my co-authors, Professor Jorge Silvestrini, here from PUC Rio Grande do Sul, Professor Eckhard Mabor from University of California in Santa Barbara, and Professor Sylvain Lazette from Imperial College London. So a dense current is a flow driven by difference in density, and in nature or in the ocean, this difference can be due to temperature, salinity, turbidity, concentration, or a combination of them. However, they are very difficult to observe in nature, so the study of this flow has been done with simplified models, laboratory experiments, and numerical simulations. This is an illustration about the flow under investigation, considering an influx characterized by its initial depth, volumetric charge, and a freshwater density plus an SX due to suspended material. Entering in an ambient with different density, it eventually will plunge and become a turbulent current, characterized by new values of depth, discharge, and density due to the continuing mixing between the ambient fluid and the underflow. And there are two necessary conditions for the plunge happen. Firstly, the influx must be denser than the ambient, and secondly, the channel must be deep enough in order to collapse the flow. The validation of the numerical framework is out of the scope of these studies. Is a complete comparison between numerical, experimental, and analytical models are available in our study from 2018. However, we aim to present an original dataset that registers the entire spatio-temporal evolution of the plunging phenomena and all relevant quantities. So the numerical methodology proposed by our previous study was a bit modified. The simulation time was extended by 20%. The computational domain is 6 times wider, and the flow variables are considered in a layer average context. And in order to support future research, all our data is available online. Here we see the experimental setup from Lambi et al. 2010. It's composed by a headbox that provides the particle-laden flow, a flume bed with angle beta, and a 2.5 meter long test section, a vent drain, and a standpipe. Our computational setup aims to mimic this experimental configuration. So the numerical domain is composed of 4 regions. First, the test session is where the flow is analyzed. IBM means immersive boundary method that includes the flume bed inside the Cartesian domain. Spawn zone A provides the particle-laden flow and a turbulent condition by means of a recycling technique. And sponge zone B is used in order to vanish turbulence level and sediment concentration before they reach the outflow boundary. So the numerical methodology is based on the resolution of the incompressible Navier-Stokes equations, in addition to n scalar transport equations and the busyness approximation. And the dimensionless flow parameters are Reynolds number, initial densimetric fluid number, Schmidt number, and Stokes settling velocity for each different grain size. The boundary conditions are defined as follows. Turbulent flow is provided by sponge zone A. Non-deformable water surface at the top. No slip for velocity and concentration at flow at the solid fluid interface. The convection equations at the outflow boundary. Periodic condition at the span-wise direction. And the initial condition is freshwater at rest. Our numerical framework allows the particle deposition but ignore erosion and or resuspension. We assume dilate suspension with no influence of particle inertia or particle-to-particle interactions. And we use the high-order Navier-Stokes solver XCompat3D. It's based on high-order finite-difference schemes. It can model a solid body inside the computational domain. It's highly scalable across high-performance computing platforms. And there is a LES modeling using implicit spectral vanish viscosity. And it's open source and available on its GitHub page. The simulations are based on 5 experiments from Lambi et al. 2010 with different values for initial flow rate, initial concentration, together with Reynolds number, initial Froude number, and 3 different settling velocities based on the experimental grain size distribution. Notice that case 2, 6, and 7 have the same flow rate and increasing concentration, while case 4, 5, and 6 have the same concentration and increasing flow discharge. Here we see an example of the three-dimensional plunging, the plunge line, and the underflow region. At the front we see the lobe and cliffs structures that are typical from this kind of flow. Here we see the temporal evolution of case 4 for 5 different times and range from top to bottom. And the plunge zone and the head of the submerged flow are visible since early times and they move downstream. And then the depth average quantities. Velocity, it's the inverse of channel's depth, so is it the case upstream plunging because channel depth is increasing. At the plunge point we see the collapse and acceleration of the flow, and the velocity is near constant at the submerged dense current. The depth average concentration decays due to sedimentation. We see the sediment Froude number as well. It's minimum at the plunge point. This value is around 0.45 here at the stable plunge position and around 1 here at the head of the submerged flow. And we can compute the bed shear velocity even though our model does not consider erosion or resuspension. We can compute it afterwards to see where it's more likely to happen. In fact, the higher value is right at the inlet where the velocity is maximum, then it decays together with the velocity, and at the plunge zone the flow accelerates and increases the bed shear velocity as well, and it's near constant here at the submerged dense current. There's an animation including the 5 cases. Here at the top left corner we have the depth average concentration. At the bottom left corner the span-wise average concentration. And here the flow quantities: depth average velocity, concentration, underflow depth, the symmetric Froude number, mixing coefficient, and bed shear velocity. Note that the dotted black line represents the plunge zone, while the white line represents the front position. So if I play with, see the evolution for all cases. Eventually the front will leave test section for all cases. And we see a lot of turbulence happen near the inlet as well as in the figures. And an interesting fact, case 2 is leaving the test section. It's critical because the symmetric Froude number is very high, so we can't keep the plunge point inside the test section. So this figure shows the time evolution for the plunge position. Then we see that keeping everything else constant, the plunge position moves downstream when we increase the symmetric Froude number, which means decreased concentration or increased flow rate. Then we see front position and front velocity, and the case that present the plunge upstream produce higher front velocities because it accelerates the flow earlier. And then the symmetric Froude number at plunge point, where we can see all cases converging to 0.45 in agreement with many references from the literature. And this figure summarizes what we saw in the movie. It presents underflow depth, concentration, the symmetric Froude number, bed shear, stress, and mixing coefficient. A good point is that a pulsing phenomenon is observed for all cases, even though the variables are evaluated in span-wise average context and the input flow was kept constant. So we see a pulsing phenomenon in all the figures. And other point is the mixing coefficient. It indicates that the underflow is incorporating material from the ambient flow when it's positive, But here for case 2 we see a negative value indicating that the underflow is in fact losing material for the ambient at around 20% near the front. So the conclusions: in this study a new dataset was presented and it's available online in order to support future research. Check it out in our GitHub page. I conclude this talk here. Thank you very much for your attention. I'm ready to take any questions now.